Okay, Itai, make your way up if you would. I was curious. I mean, both you and Douglas, UCLA faculty and fellows of the American Physical Society. Did you know each other before today?
We did.
Okay.
I was an undergrad at UCLA.
All right, so we're going to continue the theme of autonomous robots. Itai Cohen is professor at Cornell University. A little different application space, but very interested to hear what you have to say. Thanks.
Okay. Yeah, is that possible? Forward, backward laser, there we go. All right, so I'm interested in this world of microscopic robots, and today I want to give you sort of a little update on where we are on achieving this vision. And the vision is to have something like this, robots that can integrate things like a brain, maybe some photovoltaics for power, moving appendages, things of that sort, all at the microscopic scale. And this idea really originated with this very famous lecture by Richard Feynman called There's Plenty of Room at the Bottom. And in this lecture, Feynman prophesizes the miniaturization of information technology. So he tells us that the transistor is going to be miniaturized, the amount of computation we're going to be able to do will be immense. And indeed, 50 years of Moore's law, we now have line widths that are 3 nanometers. We can build absolutely amazing computational elements at a very small scale. Now, in that same lecture, Feynman also prophesizes the miniaturization of machines and tells of the amazing sort of capabilities that we'd be able to unleash if we were able to miniaturize machines. And he poses this problem because machines at the microscale are going to be fundamentally different from machines at the macro scale. That was his vision. And I'd say that on this problem, we've made much less progress. That doesn't mean that there aren't things that are happening in the world, technologies that are being developed, but we're still a long ways off from achieving the kind of amazing miniaturization that's happened in transistors. Okay, so what's the problem? So you can't just take machines like the ones that we make at the macro scale and then shrink them to the micro scale, right? We don't have nano screws, and we don't have nano screwdrivers, and we don't have nano engineers to screw the nano screws with the nano screwdrivers, right? Like we don't have the ability to make machines in the way that we do on the macroscopic scale cannot be translated to the microscopic scale. We need a totally different paradigm for making these things. And so one of the ways, and again, there are many different ideas out there. I'm going to tell you about one, which is that we're going to try to steal the fabrication tools that have been developed for the semiconductor industry. We're going to try to build our robots around the computer chips and then use origami techniques to fold these robots up into a three-dimensional structure that we can then actuate and act as our machine. All right, so that's the vision, and I just want to sort of give you an update on where we are in doing that. Okay, so if you're going to build a microscopic origami, you need really good paper. It doesn't go anywhere without the paper, and at Cornell, we are very lucky to have one of the world's premier fabrication facilities for making very thin paper. And so this is some examples of the thinnest papers that we've made. What you're seeing in the video is a single sheet of graphene. So it's 1 atomic layer thick. We've cut it up into this kirigami toy. Kirigami is just paper cutting. And you can see that it behaves very similar to what you would get if you stretched a piece of paper that was cut up in this way. We've learned how to make atomic layer deposition 5 nanometer thin sheets of paper. So atomic layer deposition is where you spray paint 1 layer of atoms at a time, and you can grow this sheet to be about 5 nanometers. If you put little plastic pillars on there and crumple the sheet, you see that it behaves very similarly to a sheet of paper that's being crumpled. On the bottom row, I'm showing you a kirigami. Now I've put cuts into the paper. That allows me to take a corner and stretch that paper out and then bring it back as though nothing happened. Okay, so now you have a 5 nanometer sheet of paper that you can stretch out and get it to expand and then bring it back to its original configuration. So we know how to make the paper, and so now what we need to do is we need to fold it. But now we have the same problem, right? Because I don't know of any nanometer scale origami artists to fold the nanometer thin paper. So we're going to have to do the next best thing, which is to teach the paper how to fold itself. Okay, so here is self-folding paper. You may recognize Mark Miskin. Before he joined Doug's lab, he was in my lab making these kinds of microscopic folding papers. And what Mark has done here is he's picked up one of these little sheets and with a tungsten probe, and by applying a voltage to the probe, he can make the sheet curl and uncurl on command. Okay, so this is a voltage-controlled folding. So how does this work? You take 7 nanometers of platinum, and you passivate it on one side with an inert material. You then fabricate your actuator using the same lithography tools we use to make computer chips. If you apply a voltage onto the platinum side, you get ions from solution absorbing onto the active side, and that creates a stress. That stress is going to bend the actuator. If I then apply the opposite voltage and drive the ions off of the platinum, then you can get the actuator to go back to its original configuration. I put rigid panels on, and now I have an origami. All right? And so what's interesting about this is that we can now drive changes in curvature down to the submicron scale. And we can do it with voltages that are about a volt in solution. All right? And so that's good because you don't want to generate any bubbles as you're bending your actuators. And you want to achieve micron scale or even submicron scale curvatures because that fold sort of defines for you the elementary building block of the robot that you're going to make. If you want to make macroscopic robots, you might be able to work with the materials that are over here. If you want to make centimeter scale robots, you would work with these materials. But if you want to make a microscopic robot, you've really got to work at this folding scale of a micron. And that's the problem that's been sort of plaguing the field. Really, we just didn't have any actuators that worked at this scale. All the MEMS devices that you've seen, those have millimeter scale radii of curvature. Very, very large curvatures compared to anything that we're talking about here. And in order to do this, we had to develop this thin film technology that could stand alone, right, off of the wafer. Right? So those are the key enabling pieces.
Question down front on your right. What's the resiliency at this level of folding? Can you fold it 10 times, 100 times, 1,000?
We'll talk about that.
Okay.
So let me just show you what we can make. These are some of the devices that we've made. This is a hexagonal fold, Mura Ori, and the world's smallest duck. And just to give you an idea of the size scale that we're talking about, if you reach up and pluck a hair, if you've still got them, and look head on, the diameter of that hair is the size, the footprint of these objects. Okay, so they're very, very small. It's about 100 microns. And we can do this with extreme accuracy. If you look over here, this bright yellow part, that's the platinum actuator. If you have platinum on top of the inert material, you form a mountain. If you have platinum below, you form a valley. And so you can make mountain-valley folds. The gray part, or the dark yellow part here, is a half-micron silicon dioxide panel. That's what gives you the rigid part. And as amazing as this bird is, it still has this wire hanging out of its butt. And so we'd like to get rid of that. So the way that you do that is you hook up a photovoltaic. Okay, so now what we're looking at is a photovoltaic that's attached to one of these actuators. So here's the photovoltaic, here's the actuator, and I'm going to show you our first ever hello world. So here it goes. We're going to shine light on the photovoltaic, and the arm goes boop, 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 boop. Okay, and admittedly this is a very small wave, something like the Queen, God rest her soul, and we want something more like an American at a football game. But you get the idea. And so now you can start to think about putting a photovoltaic for the front actuators and another photovoltaic for the back actuators. You can make bajillions of these devices. You put the pads on where you want to restrict the bending. And if you're able to do all this, then you can create this lovable robot, which Mark nicknamed Brobot. Brobot belongs on a beach somewhere. You shine light on his pectorals, and he flexes his muscles. All right? And as amazing as Brobot is, he does have some defects. All that chest hair, the technical term for that is schmutz. We don't really want that. We also tore his back legs off. That's not so good. But if you work hard to solve these problems, and Mark did, you get this robot. This is a 40 micron by 70 micron by 2 micron robot. It folds itself up, and then by shining light on the front and back photovoltaics, you can walk this robot off the Petri dish. And this is, at least was for a while, the world's smallest walking robot. We've recently demolished that record by a couple orders of magnitude. So as amazing as this robot is, it is still just a marionette. Right? In a marionette, you have strings that are pulling the arms and the legs. In this robot, we have lasers that have to point at those photovoltaics. And so the question is, how do we get off of the strings? How do we allow this robot to be more autonomous? And the answer is that you make a robot brain. And so now the idea is that you put on simple controllers that can generate the pattern for the leg motions. And if you do this, this is what it looks like after an immense sort of development process where we were able to take some of these electronic chips that we made in a commercial foundry and then connect them up to the legs that we made in-house in order to make this robot that we call AntBot. And in this particular case, AntBot, you just put it in the Petri dish and it walks on its own. Okay, so you don't need to do anything, you just shine light on, and this thing will generate this tripod gate where two legs from one side and one leg from the other side move with opposite phase in order to create this gate. All right? So AntBot is a completely autonomous robot. You just put it in light and it does what it does. In the same way that the Marvel universe has metastasized, at Cornell, our little microsystems universe has metastasized. And we too have a bunch of different directions that our robots have been going into. And so I'm not going to be able to tell you about all of these directions. Maybe I'll just show you a few examples, and I'm happy to discuss any of them in more detail as you wish. So I've told you a little bit about the autonomous microscopic robots. Let me tell you a little bit about some of the ideas that we have for augmenting surgical tools. So here we had to solve a materials problem, and the materials problem is the following. If I take the platinum, the ions that absorb onto the surface of the platinum, even if we oxidize the platinum, it only affects the very surface of the metal. And that means that if you want to make a strong material, which by definition means you got to make the film thicker, then you sort of lose the oomph for the bending. Okay, oomph is a technical term, right? Your moment arm shrinks. So what ends up happening is that you don't have enough bending stress in order to sustain that micron radius of curvature, and so now you're in trouble. So to solve that problem, we had to develop another material platform for strong actuators. And there, the idea was to use palladium instead of platinum. Palladium is a bulk absorber of hydrogen. So that means that if you apply a voltage, you can actually get hydrogen to absorb throughout the entire material. And so if you make it out of half palladium, half titanium, then you can maintain your bending oomph, as you make the film thicker. And so now we can make 400 micron thick films, 400 nanometer thick films instead of 10 nanometers thick. That allows us to now operate in tissues with comparable modulus to brain tissue. So this is what these films look like in the transmission electron microscope. You can see there's a lot of material science here that needs to be done to kind of make this a commercial product. But right off the bat, it already performs extremely well. Here's an example of a little arm or, I don't know, hand that can essentially clasp, and the material that it's moving through is a gel with the stiffness of brain tissue. And so it's easily able to adjust the little leafs in order to bring those bubbles closer, and so it can operate in that kind of environment. We've thought about how to use this. So again, here, just to be clear, the actuators are these little bright yellow strips, and the dark yellow is the solid silicon dioxide panels that we're moving. This material, this palladium actuator, has a number of interesting properties. It operates at an actuation voltage that is about a volt. It has an energy density that's the highest of many of the materials that you use for actuation. It's comparable to shape memory alloys, if that means anything to you. And it has a bending curvature that is, again, submicron. So it's a very promising material and another interesting platform to try to build robots from. What we're thinking about is how to replace devices that currently look like this. This is a little tool that is a piezo. A piezo is another type of actuator that would be used, for example, to guide a laser beam at the end of a fiber. That piezo is just under a centimeter in size, and this might be threaded up your urethra in order to do surgeries inside the bladder. And our question is, could we start to think about using these smaller actuators at the end of a fiber that's only 100 or 200 microns in thickness, right? So an order of magnitude smaller in size for operating. Those fibers would probably bend pretty easily, but there are ways now for embedding magnets at the tips of these fibers in order to guide them to the locations that you're interested in. Here's an example of one of our robotic attachments on top of a 200 micron fiber. The fiber has metal wires that are threaded through it, and by attaching it, this is again our hello world. This is about as far as we've gotten here, but you'll see in the video that these little elements at the edge here can be moved by applying voltages through the fiber. Okay, and so those are sort of the appendages that you're now going to be able to have at the 100 micron scale and lower as you try to manipulate whatever it is that you're doing in your surgical arena. We've also made a robotic arm. So here what you're seeing is an arm that can swing, lift, twist, and grasp. And what you're doing here is you're essentially threading wires through the various hinges, and those wires are not doing any of the bending, so they're just transmitting the information to the next hinge that's down the line. And so you can start to think about how to wire different functionalities into the same robot or robotic arm by doing things like this. I'll tell you a couple of other stories. This is an interesting one. It's kind of a far out idea. The question is, can we make an elastronic material? And you're probably thinking to yourself, what the hell is an elastronic material? And so you probably have heard of metamaterials. Metamaterials are materials that sort of combine two different materials or some sort of structured, in some sort of structured way in order to create properties that you couldn't achieve with one material on its own. You take a piece of plastic, you cut it up in a certain way. Now it's made up of both the cuts, which is air, and the plastic, and you can deform it in ways that you couldn't deform the plastic sheet. And so our idea is to do the same thing with these kinds of microscopic systems. And so we can create origami linkages, things that allow you to bend or splay two panels. So the idea would be to print a sheet in 2 dimensions, and then through local expansion, that sheet would be able to locomote and maybe even wrap something in order to clear it or destroy it. And so the idea here is that, again, we're going to use our actuators to make a very simple origami linkage. In this case, you're splaying these 2 panels by hiding material at the back of the hinge more than at the front of the hinge. So it's a mountain fold with 2 valley folds that allow you to do that. This is, and then the idea is that you could put these together into a unit cell and then a full-scale sheet that through differential expansion of different elements inside the sheet, you could form different shapes. So here's what the individual splay looks like. This is confocal microscopy data of an actual device splaying. This is what a hexagonal unit cell looks like. You can see that the area of the cell is different when it's closed versus open. And this is what a full sort of sheet looks like when we've pinned the edges. And you can see that if you expand the center but the edges are pinned, then the sheet has to pop out into the 3rd dimension. That's how you get your Gaussian curvature. And so now you can start to do this with different components. You can have an inside and an outside. So here I have an inside piece. If I actuate that, I get this nipple. If I have an outside piece and I only actuate the outside, I get this furly sort of flower pattern. And if I actuate both, I can get the full expansion of the sheet. And so this gives you families of shapes. And by breaking symmetry, having a front and a back, you could try to then create locomotory patterns. And so this is an example of a robot with a front end that has a different boundary condition from the back end, and that allows the robot center of mass to translate as you actuate these cycles. So what is an elastronic material? What we're trying to do is we're trying to put electronic elements on each of those panels. That would allow you to completely control each hinge separately. And so there's a whole infrastructure that we're trying to develop where we're now putting electronic components on each panel and having them talk to each other, synchronize their behavior in order to produce locomotory patterns or some sort of other behaviors in the sheet. So we have the electronics from other projects. We have this particular sheet. We've also shown that we can synchronize the electronic components. And so now we're putting it together into this elastronic material. And what's interesting about elastronic materials as a concept is that, like in most materials, you might need to, if I whack a material on one side, the information would propagate at the speed of sound, and you'd be able to feel it, some time later. In an elastronic material, if I get whacked on one side, I could transmit that information at nearly the speed of light to the other side of the material. That would allow me to anticipate what's coming and react before the sound wave even gets there. And so there's all sorts of opportunities for interesting innovations in materials and trying to think about how to even sort of take advantage of these properties if we could do this kind of, if we could make these kinds of elastronic sheets. The last thing that I'll tell you about is a new technology that we developed, is an actuator that works in any material, in any environment. So the idea is the following. Here we're going to carry the charges inside the material. So we're going to have a platinum sheet, an ionic conductor, and another platinum sheet. And when we apply a voltage across the platinum electrodes, we can drive ions in the ionic conductor to one side or the other. So if we drive oxygen to the top, the sheet will bend down. If you drive oxygen to the bottom, the sheet will bend up. And that now means that you're carrying the charges inside the material. You don't need a fluid to operate in. So these could operate in air, they could operate in vacuum, they could operate in fluid, in any environment that you want, as shown by the bottom pictures over here. So here's an example of a tantalum oxide and a hafnium oxide hinge or sheet. And what's interesting about these is that they have different time scales depending on the operating voltage. So for example, if I operate this at 3 volts, I get this sort of very, very long time scale for the charges to drift to one side or the other. If I operate it at 8 volts, then my time scale is very short. All right, so if I want very fast actuation, I need high voltage. If I want slower actuation, I could do it probably at 3 volts. And so that's what's shown over here. And now what I'm showing you is, as a function of frequency, what happens. And so if you're at 3 volts, if I start operating at too high of a frequency, the ions just don't have enough time to reach the other side of the actuator. Okay, so if I go to high enough frequency, my amplitude of actuation decreases because I haven't really moved the oxygen atoms enough in order to get any bending, okay, over that time scale before I start switching and now the oxygen atoms are moving down. Okay, so that up and down motion doesn't go anywhere. If I'm doing it at 8 volts, I can I can go to higher frequencies, but it also has a roll-off somewhere at 1,000 hertz. That is important because the next thing I'm going to show you, what we wanted to do is we wanted to use this for like actuators for a wing, for a micro-air vehicle. And if you want to operate a micro-air vehicle at the millimeter scale, you really need to operate somewhere at the 300 hertz range, something like a mosquito wing, like a fruit fly is at 200 hertz or something like that. But here's the problem. So you're going to need to work at 8 volts for that high frequency, but at 8 volts you only get about 20 cycles before this actuator craps out. If you work at 3 volts, you can get to 10,000 cycles. That's still not great for a 300 hertz vehicle. That's going to crap out after a few seconds. So it's not amazing yet. Now there's a lot of material science that we need to solve, but we had one more trick up our sleeve, which is that if you start working in that regime where you don't get much actuation, but if you're at resonance, then you can actually do pretty well. So what's the idea? The idea is that you're going to work at a high enough frequency that the oxygen atoms don't go anywhere. That means that you can't carve out that short between the platinum electrodes. But if you operate at the right frequency, you can excite a resonance in your actuator. That allows you to achieve the same amplitude, okay, large amplitudes, but now without crapping out your resonator. And now you can achieve something like 200 million cycles, and that's just because the student was tired and had to go home at the end of the day, right? In principle, this should work now for a very, very long time. Okay, in fact, like a good, you could probably operate for 2 weeks in sunlight, no problem.
Why doesn't resonance pose a large threat to the structural integrity of the material?
Yeah, so if you have a beam and I want to bend it, okay, this part has to stretch and this part has to compress, all right? But if I shrink that beam down, there's this beautiful line right in the center where it neither compresses nor expands. And so the thin films allow you to operate for very, very long times because you're not actually stretching the films by very much. Okay, so that's the beauty of working with metallic systems. They have a high modulus and they don't allow you to stretch very much. You can't do what you do with polymers, but you don't need to because you make them thin enough, you still win. They don't expand by more than 1%, and then you don't have any problems with dislocations and all the rest of that stuff. Now, it doesn't mean that there aren't problems like in the 200 nanometer devices or 400 nanometer devices with palladium. There, we can go for 1,000 cycles, and then it craps out due to materials issues. And so we're working on that. But there are lots of cases where if I need to do a biopsy operating a few hundred cycles is fine. So it really depends on the engineering purpose, but that's why we can do this type of thing for an infinite number of cycles. So with that, that was actually in vacuum, and we were then able to construct a wing with the right mass and figuring out the viscosity that would feel in air, that would resonate in air. And so that's what you're seeing in this video. Can you guys play the video for me? Maybe no, I cannot. Let's see. Maybe you can see it there at the bottom right. That is a wing that's operating at 300 hertz, and it operates for hundreds of millions of cycles. Okay, again, because the student had to go home. So that's the idea. And what's interesting about these flyers, I'll just say one more thing that's interesting. If you take a look at robotic flyers, like your drones, they work really well. But if you want to miniaturize them, you run into trouble. So the smallest single blade rotary drone is about 2.5 centimeters. That's piccolomissimo. And if you want the flapper, the smallest flapper is RoboBee, and that's on the order also of a few centimeters, about 5 centimeters. Neither of those work for very long. Like the battery technologies on those run out within a few minutes. So you could do things like charge them every few minutes, but you could do better if you miniaturize things further. Why is that? Well, the lift forces that you're getting from the rotors scale like L squared. It's the area of the wing. The force that you need to lift the object goes like L cubed, the mass of the object. So if you go to smaller scales, you could actually get enough lift force, okay, if you just had the power of the sun. And the reason they don't do that is because we don't actually have actuators for that scale, okay, for the millimeter scale. It turns out a millimeter is where you win. Okay, if you can make your rotor down to a millimeter in size, then you would be able to sustain your air vehicle for ever under sunlight. All right? And so the reason they haven't done that is because the materials haven't existed. And I think this is a good candidate material. It could allow you to function over very long periods of time and under the power of under one sun. Okay, so those are some of the things that we've been doing, and I would say that this is really only phase one, because what I've talked to you here about are the mechanical elements. This is really just the exoskeleton, right? What's coming next is going to be the computation. The very simple controllers that I showed you for the microscopic robots, those were done with 180 nanometer line width. And what we're gearing up for now is trying to miniaturize the electronics and trying to figure out what sort of stack would we really ideally want in order to get these robots to start functioning as independent agents that could maybe be sent out into the field to operate independently, maybe have them search for some sort of fungal infection on a leaf in a field. What would it take for them to start signaling to each other that they should gather around and start to act to either get rid of the fungal infection or maybe communicate to the outside world that there's a fungal infection or something of that sort. And this sort of paradigm of search, gather, act, that can be applied to lots of different places. Could you hunt around for cancer cells in an incision and be able to gather other robots to then irradiate those cells and try to eliminate them? So all of that sort of stuff is on the horizon in the next phase.
Sounds like this can be used as a weapon also.
I think with every technology, there is the capacity to use it as a weapon. I think that's a serious question. You take the robotic flyers, they could be used to explore space. They could be used to be sent into dangerous environments to look for things. But they could also be used as listening devices. And
I got the idea from a novel I'm reading.
So it's not so far, is I guess my point. What would we want this technology to enable? And I think really the answer is anything that you can think of at the macro scale has an analog at the micro scale. At the macro scale, we use robots to clean our surfaces. That can be done at the micro scale. Maybe you're cleaning a fabricated tissue from a bacterial infection. Maybe you're using these robots to modify their environment or assemble some sort of object, or carry cargo from one location to another, organize their space, allow us to access surgical environments that are too difficult with current technologies, and really explore the microscopic world in a way that's fundamentally different from just sort of the observation from above, which is what we typically do with microscope lenses. We can now think about these as appendages to those lenses that can receive information through those lenses, act on the microscale as appendages, as mirrors, as devices that allow us to really explore the microscopic world in ways that we couldn't really think of doing before. That's the vision, and that's sort of where we are. I think it's amazing that Mark's first paper on the electronic microactuator, that came out 5 years ago, right? And we are making very rapid progress in a way that is very evocative of that quote, underestimating what we can do in 10 years. I think I vastly underestimated what we could do in 10 years, and I'm excited to see what the future holds. So thank you.